there was one question just now, which I think is useful to tell everybody. How's const read-only access of a view described? Basically by making the data type const, right? So instead of having view of double star, you do view of const double star. And that then means that the pointer internally is a pointer to const data, right? And that then goes all the way through the stack. Okay. Okay. So the next thing I want to talk about is managing memory access patterns for performance portability, and that's where we're also going to come back a bit to the, the false sharing stuff. So in particular, I want to talk. If you think about the YAX thing, right? An interesting question is, how should have A been laid out, right? And that's what we're going to talk about here. We'll talk about the view's layout parameters. We talk about the memory access patterns, which then, and how that in conjunction with how Kokkos schedules work leads to decent memory access patterns, why that actually is really important, and see a concrete example of that. Next slide. So think about that example, right? An interesting question for this thing is, right, how should A be laid out in memory, right? Can you click? And there's, for matrices, there's like two typical things, right? There's this column major and this row major layout, right? And in Kokkos, we call them slightly different. We call them layout left and layout right in the previous slide. The reason that we call them layout left and layout right is that column major and row major only really make sense for 2D. Layout left and layout right make sense in higher ranks. And essentially what layout left means is the leftmost index is stride 1, and the layout right means the rightmost index is stride 1, and they monotonically increase. What you do with that parameter is you use that as an additional parameter to your view. And if you provide that layout parameter, it comes before the space argument if you have both. The most commons are, as said, layout left and layout right. If you do not specify a layout, then we choose a layout which actually is deduced from the execution space of the memory space you're using. So, you have their space argument, and we figure out what execution space is the primary associated execution space of that memory space. And then we use its, preferred layout. You can actually write your own layouts. The way you do that will actually change with the current work we're doing for MD-span in there. With MD-span, it actually becomes a bit easier to write your own layouts. So, you may want to wait for it. But there's some advanced layouts we provide, for example, layout stride and layout tiled and some other ones. The layout stride in particular is important when you want to get like subviews, right? If you think about like the kind of capabilities in MATLAB or Fortran where you can get like a subarray, that array might have arbitrary strides, right? Depending on what you get. And so that's what layout stride is for. Next slide. What this exercise can do is you can change the layout of A, right? And then essentially check for the impact of that. And if we go one slide further, that is essentially the benchmark, right, for this thing. So what I'm doing here is I'm running the matrix A has the same number of elements, but I'm changing the number of rows, right? So I always have like, I don't know, a matrix of a couple hundred megabytes, but I'm changing how many rows I have, right? So if I increase the number of rows, the number of columns goes down, etc. And then what I did is I run that on, and I think in this case, I run that on a Pascal GPU, KNL, which is what you have on Theta, and Haswell. And I ran that with using layout left and layout right. Layout left is the dashed lines, and layout right is the solid lines. And what you see here is that the performance difference is quite stark, right? You see that the difference between the two blue lines, right? At its worst point, I think if you look at the exact numbers, it's something like 30 or 40x or so. It's only about like 5x or 4x for the GPU. So it's actually more important on the CPU to get the right layout, the correct layout. But the interesting part is that the GPU wants layout left and the CPU type architectures want layout right. Okay. And the question is why? Okay, next slide. And one way to think about that is thread independence. There's other ways to think about it. For example, on the CPU, we can think about that in terms of like false sharing, right? But from a GPU-centric perspective, we'll start with the thread independence. And so one question you can ask yourself is, right? So say I read D, right? I read an element here from a vector. Can I immediately continue, right? And the answer for that is on CPUs, yes, right? All these threads are completely independent. They execute at any rate, you know, what we can do. So we can just go on. On GPUs, that's not necessarily true. On GPUs, threads execute in these you know, groups of like warps and stuff. And the memory operations are actually memory operations, which are kind of collective operations of threads. So when you issue a load on the GPU, you actually issue a load like on NVIDIA, for example, say 32 byte or 60 byte, depending on the size of the thing. On AMD, it's actually even wider. And essentially, this thread needs to wait until every other guy also has its thing loaded. Okay. Can you go on? Now the question is, how many cache lines did we need to load, right? Go on. And if you think about that, right, about the independence as well as the sharing, right? If you have a caching architecture and you want, you know, what you want is that if you loaded an element in some thread, you know, on a CPU, then the next load you load, right, should come hopefully from the same cache line, so you already have that cache line there, right? So that means only every, you know, 8th or 4th or 16th or whatever load, depending on the cache line size, needs to actually load a cache line into your memory. On the GPU, on the other hand, you want what we call coalesced access. So that if you read with a thread a value, right, and we said that, you know, it's doing one load instructions or combined load instructions with all kind of its associated threads. It would be good if all these threads access the same cache line, because that means that combined load instruction only needs to load that single or maybe two or whatever cache lines. So what that means in caching, if thread T accesses its current access at position I, then its next access should be at I+1. For coalescing, what you want is if thread T accesses position I, then thread T+1's next access should be at access should be at position I+1. Okay, can you click? And if you have uncoalesced access or non-cached loads, you know, on CPUs and GPUs, if you have the wrong thing there, right, you essentially are kind of toast. Okay, next. So, and that's what layout left and layout right do, right? If you assuming we have a fitting scheduling. And the rule of thumb in Kokkos is that the way we do index mapping to execution resources from our Parallel 4 and our default layouts work, that if you parallelize over the leftmost index, right, you get caching on CPUs. And because, you know, caching implies that we don't have false sharing, right, because we hand indices out in a way, you know, that the next access comes from the same cache line, right? So that implies that, you know, threads don't access each other's cache line, right? So you don't have a false sharing. But essentially, we choose these things so that if you parallelize over the leftmost index, right, and you have everything defaulted, then you get coalescing on GPUs, and you get caching and no false sharing on CPUs. Okay. Now, obviously, it's not always quite as simple. You know, sometimes there is, you know, you need different layouts and different algorithms and stuff like that. And in some cases, you know, you just have to make compromises. The nice thing with Kokkos is that it's just a change of a template parameter, right? So that means you can recompile your code and it's at least functionally correct. If you did proper type defs in a single place where you can just try out, what is the best thing if there is no obvious way to tell, right? Okay, next slide. So, and that's what happened in that example, right? The CUDA space by default uses a layout left, while the kind of CPU architectures use layout right. And what that means is you're getting column major on the GPU, and you get row major on the CPU. But as a consequence, right, this inner loop there, which runs serially, right, on the CPU, you go through consecutive memory elements, while on the GPU you stride because you want the coalesced access on the column index, because every thread has its own kind of row. Okay, next. And that's what you're getting here, right? You get coalesced access with layout left on the GPU, and you get cached access on the CPU with layout right. Okay, does that answer the question about the false sharing? Probably. Yeah, no, I'll hope so. Okay, next slide. So the summary is that every view has this layout parameter, which is set through a template parameter, with layout right and layout left being the most common. And views in kind of host space default to layout right, and views in most of these GPU spaces like CUDA space and HIP space and SYCL space and OpenMP target space default to layout left. You can write your own layouts. We're not even quite as restricted as this implies here. For example, layouts don't need to be unique. So it's actually legal to write, for example, a layout for symmetric matrices where you only store, like, say, the upper half, but you can still index, I, j, and the layout underneath does that. Kokkos views and MVSpan essentially have properties attached to them which tell you whether something is, unique or not. So, things like that are possible. I even once wrote a thing for like a layout for kind of a cycle buffer where essentially the first index was just like a mod 2 or something like that, right? So that I, in independent, in consecutive iterations, just went through, just cycled back and forth between the two actual things. For performance, you need these memory access patterns must result in caching on CPUs and coalescing on GPUs. Tools help you with figuring that out. For example, on GPUs, whereas this property of like access efficiency, essentially the difference between what we call requested global accesses versus actual global transfers, and so you can see whether you do something wrong there. And what we do by default is we try to map parallel work indices and the multidimensional array layouts by default such that you end up with performance portable memory access patterns if you parallelize over the leftmost index, right? And there isn't really anything in OpenMP, OpenACC, or OpenCL to do that, right? To manage these layouts, you essentially need to, you probably need to write that by yourself, right? Either through multiple versions, or you write essentially the equivalent of a Kokkos view. Okay, next slide. So the last thing I really want to talk about here before we go into the exercises is hierarchical parallelism. And hierarchical parallelism is a rather critical feature because it's needed often to essentially find and exploit more parallelism in your computation. Generally, as a hint, as a hierarchical parallelism allows you everything all the way to effectively warp synchronous programming, and actually sub-warp synchronous programming, or the equivalent of thereof, just in a, I think, nicer way. And I want to teach you here a bit about the similarities, between like nested parallelism and outer parallelism. We'll talk a bit about the thread teams. We'll talk a bit about, performance improvements you can get with that. Typically in our applications from, as kind of a rule of thumb, about 2/3 of our loops, I would say, are simple range policy loops. And a good chunk of the rest is hierarchical parallelism, and then there's some which are like, multidimensional range policies. There's another, I'm not going to talk about that today, but there's one which essentially just for tightly nested loops. The hierarchical parallelism, however, is the one which is pretty predominant in our most important kernels and the most time-consuming kernels, largely because the most time-consuming kernels are often also the most complex, and you need the flexibility of expressing parallelism on like multiple loop levels, and this is what this is for. Okay, next slide. So let's think back about, in this exercise, right? And what we did there is we parallelized over the number of rows, right? We parallelized over the column index, and then just had a serial loop over the row. Okay, click. Now, the problem is, what happens if we don't have enough, rows to saturate the GPU? And you saw that in the benchmarks, right? If you look there closely, and I'm going to come back to that in a second here, so in a bit later. You needed on the order of, I think, almost 100,000 rows in order to make the P100 GPU, reach max performance. So what if you don't have that, right? But maybe your rows are actually pretty long, right? Then you don't expose enough parallelism right now. And so the question is, how do you resolve that, right? And there are a couple of possibilities, right? One thing is you can flatten the whole thing out and then use atomic updates, for example, but that's probably rather conflict prone, and so performs reasonably bad. The other option here is we use these thread teams, right? Okay, click. The atomic stuff, as I said, I'm not going to talk too much about this here. Basically, it's just, as I said, it's really scalar integration with atomics, which is kind of stupid. But what you could envision is that what you really do is for each row, we do reductions, right? The inner loop here is the parallel reduce over, or it's a reduced kernel over the row. Now, what this really is this is an example of hierarchical work, right? For each row, you do something. And essentially, algorithms that exhibit this kind of hierarchical structure or hierarchical loop structure is what can benefit from these thread teams. Okay, click. Using a team is changing the execution policy. So in this flat parallelism, right, we had just this range policy, and we specified the total amount of work. Right, that was what we did. We did this range policy, maybe with an execution space argument, maybe without it, and a begin and end. Click. In hierarchical parallelism, we use what we call a team policy. And what you specify there is you specify the number of teams and the team size. Now, the team size is limited by hardware properties, largely because within a team, we want to be able to synchronize, which means we also need to kind of be able to actually execute all of the team ranks, at the same time. The number of teams is not limited. That's an algorithmic parameter. And this is directly equivalent to what they call leaks of teams, in OpenMP. Okay, click. When using these teams, your functor operator now doesn't get an index. What it gets is it gets a handle to one of these team members, right? And what you can do is you can ask this guy, right? You can ask it, which team do I belong to, right? What is my league rank? You can ask it which thread I'm in within that team by asking it for its team rank. You can ask for its league size. You can ask for its team size and other stuff. But one thing to keep in mind here is, right, this team size is not directly related to any of the internal loop lengths, right? You just get a number of threads, right, which can do shared work or collaborate on work. Okay, let's go on. So the point is that you shouldn't hard code, work mapping on the nested loops either, right? We didn't do that on the big loops, right? On the big loops, on the top level global loops, I never told you how to get a thread index. And in fact, you cannot get a thread index in Kokkos, right? For the range policy, we do not give you a capability of asking what thread I am. The reason is that that would essentially lead to thread-centric programming, which, for example, would prevent us potentially from, by default, telling compilers this loop is vectorizable, or mapping it to things like pipeline architectures, which do not have threads. So what we now want to do is, right, this nested loop. So we start this thing with the team member, right? We say the row index is now the league rank, right? We assign each team to one row. And then we want to do that reduction, right? And it's essentially a reduction over m columns. And, if we were encountering that as like serial code, we would say, oh, this is a parallel reduce, right? It's a parallel pattern. Click. And, the point is, it is. Click. Right? This is parallel execution again. It's a nested parallel pattern using the parallelism or exposing parallelism to the team. Okay, next slide. So what we do is we use the same parallel reduce pattern. The only thing different is here we use a different execution policy. And the execution policy we use here is the team thread range, which takes this team member and then a count or a begin and end. You could say 0, m here. And what the team thread range says is, it essentially says, split this range over the threads of this team, right? Distribute the range over the threads of this team, parallelize it with that. And that's what this does. Otherwise, it looks exactly the same syntax, right? It takes an index, it takes, like with range policy, it takes an index, it takes for reduction a thread local variable, and the parallel reduce takes as a third argument the place where to store the final result. Okay, next slide. Again, the mapping of work indices to threads is architecture dependent, right? Essentially, the same rule of thumb I said earlier for range policy applies here for the nested pattern, right? If you, before default layouts, right, it would be parallelizing over the leftmost index would lead to coalescing and caching, for team threads. The amount of work here you give, right, with m doesn't need to be a multiplier of the team size. The same way as, range policy doesn't need to be a the range doesn't need to be a multiplier of any of the underlying thread backends. And the intra-team reduction here is handled by Kokkos. Click. So how does that then look like? You have this, generally you can mix and match that stuff, right? You have this outer parallelism, you give it this team policy, they tell it, how many teams and the team size. Then your lambda gets that team handle, and then you can use that team handle to launch inner parallelism, right? And these inner parallelisms can be, parallel force, reduce, or scan. I think we have not implemented the outer parallel scan for team policy because we have never really found a good use case for it. One thing about this is you can have multiple of these inner parallel loops, one after another, right? You cannot just have one, but you can have many coming one after another. And they can be different types, right? You can have first a parallel 4, then a parallel reduce, then another parallel 4, so and then a parallel scan. That works. What you cannot do is you can't nest another parallel, the team thread range inside of an existing team thread range.
So Christian, maybe a quick question. You don't have a 3 level, you have only 2 level parallelism.
No, we have 3 levels.
Oh, you have 3 levels. Perfect.
Yeah, we have, I don't know, I think the slides actually will at least mention that if we go further. we essentially have the team, the threads, and the vector level, and the exact equivalent of our loops is actually, as what we think is the right mapping for OpenMP target would be, the kind of leak thing. Then, as the outer thing is the Pragma OMP distribute, teams distribute. The next one is the Pragma OMP4, and the one after that is Pragma OMP SIMD. And I come to that in a second, why it's not Pragma OMP Perl 4. Can we go to the next one? In practice, one of the questions you have is, okay, what is the team size I should choose, right, for this stuff? In practice, you can let Kokkos decide, and you can use this Kokkos Auto. And we have a heuristic there, which will choose some team size. But we also have auto-tuning tools which can do that. In practice, right, on GPUs, you want rather larger teams, right? Typically, 128, 256. You want them a bit larger on AMD than on NVIDIA. Our internal heuristic right now essentially takes into account things like register counts, as well as, I haven't talked about that yet, like shared memory usage, etc., to find a team size which leads to optimal occupancy. On CPUs, on pure CPUs, it's often that team size 1 is the best. The reason is that if you have multiple threads in the team, right, you need to synchronize, for example, on a reduction. And it almost never is worthwhile on pure CPUs to have that additional synchronization cost, even though it might help you with better collaborate on sharing the cache, right? Instead of like each having a row, of the metrics in cache, in the same cache, say the 2 hyperthreads on a single core on Skylake, right? You could have just 1 row in cache and work on it, right? But the caches are so big, that usually it doesn't help. On Xeon Phi and architectures with more hyperthreads than 2, it does reasonably often make sense to use a team size which is roughly the hyperthreads per core, right? Because then you don't fight over cache resources and don't like split the cache into more little levels. Okay, next slide. There's an exercise we definitely won't come to that today, to essentially convert that little, example into like hierarchical parallelism. Go to next one. And this is what we remember, right, from exercise 4. So this was the range policy. And what you see here is what I said earlier, right? But you need 100,000 rows in order to get maximum throughput, right? And you had layout left on GPU good and layout right on CPUs good. You see on the Xeon Phi, I needed 128, or so for like best throughput, which was like 2 hyperthreads per core, I think. And on the Haswell, it was just 16, right? Every thread is used. Okay, but now we change to the thing. And what you see here, if you look closely, for the GPU, the optimal point, right, where you reach maximum throughput moved quite a lot up, right, as a forward, right? So you need now only about 1,000 rows in order to make this reach full performance, right? On the other hand, you lose performance on the right side. The reason is partly that is because I'm not fine-tuning. So I could extend that a little bit by fine-tuning. But the problem is where essentially the rows get really short. And so having a whole team, of like, say, 128 or whatever threads running that doesn't make too much sense. On top of it, you're now paying, the amount of cost you have in terms of doing these kind of combined reductions on each team, right, is starting to get much higher, right? Before, you had just the thread summing up into a scalar. Now you actually need to do a full reduction in each team, right? The other thing here is, if you look at this, that layout right is now also the correct layout for the GPU, right? And the reason is that you parallelize over the inner loop, parallelizes over the rightmost index, right? And that is now the index where you need the coalesced accessing. The good thing is it's just the type def on the view. Okay, can we go? Next slide. There's also vector level parallelism. It's an optional third level in the hierarchy, and that is what you would use for like thread vector range, and you can use that with parallel4, parallel reduce, and parallel scan. And what that does is it maps to essentially vectorizable loops on CPUs or sub-warp level parallelism on GPUs. The way you do that is you give a third parameter where you essentially say, what the vector length of choice is. It can't be larger than a warp, but it can be smaller. You do not get explicit access to the vector lane ID, so the only way to use this is via vectorizable loop, right? While in principle, you could use team level parallelism by just doing your own index calculation using the team rank, right? But you can't do that with the vector lane. Now, one interesting problem, right, is that depending on your backend, right, these vector lanes might be redundantly executing the entire time. On CUDA, they are, right? From the first instruction inside of your team thing, right, every vector lane executes this. On CPUs, we are not, because in CPUs, you get implicit vectorization through the compiler just on the vector loops, right? And I'll talk a bit about how to resolve that problem or where that leads to problems in a second. There's also a team vector range, which essentially combines thread vector range with team thread range, right? So you use both levels of parallelism for a single loop. So you could have, next click. So you can have something like this, right? Where you have a team policy on the outer thing, then you have a team thread range, then you have a thread vector range nested in that thing, and then at the same level as the team thread range, right, you have a team vector range, which essentially uses both levels of parallelism, right? And again, you can have multiple of these loops, right? You can have multiple thread vector ranges within that team thread range. That's not a problem. And they can be these different things, parallel force, parallel reduces, etc. As I said, you don't need to use the full 32 byte for a thread vector, right? So, for example, for our sparse medvec implementation, we choose the vector length depending on what the average row length of our sparse matrix is. And typically we use roughly the closest power of 2, which is roughly a third of the vector length. So for a typical kind of mini-FE thing, for example, the vector length would be 8. And Kokkos implements that correctly, right? So if you have a vector length of 8, then in CUDA terms, each CUDA warp actually has 4 Kokkos threads, each with 8 vector lanes, right? And our reductions and stuff like that all implement that correctly. Can we go one further? Now, I said that everything kind of redundantly executes, right? That means you need to restrain certain execution from actually happening. For example, you want an atomic add, right, outside of a vector loop, and you want it once per thread. What you need to do is you need to protect that. And what you protect that with a single pattern. That's actually kind of the same concept as OpenMP single. And the single pattern takes also an execution policy, and that policy is either per team or per thread. So per team would mean that only one vector lane in the entire team will execute it. Per thread means that for every thread who calls this, one vector lane will execute that. And it's equivalent to OpenMP with a single directive with no wait, in some sense. Okay, can we go to... let me talk just 1 second more about, before we go to the exercises, about why we do redundant execution. So one problem you have, right, if you, and this redundant execution is also true for the threads, right? I said you can ask for the thread ID, outside of the team thread range, and you can just ask the handle. That's why the team thread range is the equivalent of a pragma OMP4, right? The threads are already active. You are just distributing a range over these things. And we don't even synchronize at the entry to the loop or the exit to the loop by default, right? It's the equivalent of a pragma OMP4 no wait. And the reason we do that is to avoid unnecessary synchronization inside the code, but also if you actually were to do in OpenMP, right, with teams parallel stuff and then a pragma OMP parallel 4 as nested loops. What needs to happen is that each thread gets the state of the master thread. And the way, for example, the XL compiler used to implement that is that it would, at the entry to the nested loop in an OpenMP target region, it would dump the state of the master thread, its entire register state, into global memory. Then every thread of the team would load this thing into back into registers and start executing the nested loops. At the end of the nested loops, you would dump the state again and restore the original state. Okay. Obviously, if your nested loops is something like our team vector range or little reduction over a small row, right? The register dump and reload actually completely dwarfs any of the work you do inside of this thing. So that approach is significantly slower than just having all the threads redundantly execute a couple of instructions before and then just split the loop. And that's also how CUDA works, right? In CUDA, all the threads are active all the time, right? And yeah, so that's why we do that way. It's just something to keep in mind. Okay, there's this exercise here, which is a slightly extended version of the one we had before, which essentially it does the same problem we just had, with like the y times ax, but it does it for like a range of elements, right? So it introduces a third level of parallelism. And can we go there? And if you compare that, you just use like team parallelism versus you use team plus vector loops. What you see is on the CPUs, it doesn't really make too much difference. Other than on like KNL to a total right? But if you are in that regime, it makes a big difference, right? If you look at the roughly halfway between 100,000 and or 10,000 and 100,000, there's 2x difference in performance between the 3-level version versus the 2-level version, right? The blue lines here, the dashed blue lines versus the solid blue lines. On the GPU, you get benefit throughout, with like 20–30% or something. But the point is, unless you are in a regime where you really need the 3-level parallelism, because otherwise you don't have enough parallelism available or whatever, it's more of an optimization, right? It's not kind of a game changer. That makes sense. There's a question that the nested thing here has reduced the peak bandwidth a bit. Yes and no. The problem is that the thing is not quite 100%. It's not fully comparable, right? These things are actually different algorithms, so we are not like one-to-one Apple comparison, because the original algorithm didn't have like a third level of parallelism. So I can talk about that, but basically, as of yeah, I think it's not too important to right now go into details. There's no intrinsic reasons that you couldn't, with the third level of parallelism, get the maximum peak bandwidth, right? And we actually, the way our SPMV is implemented, it actually uses 3-level parallelisms for this stuff. So as the most important kernel we ever execute, in our environment is using 3-level nested parallelism. Okay, can we go next slide? So what I hope you got away from this is that if you have this kind of hierarchical work, you can be parallelized by a hierarchical parallelism, and that hierarchical parallelism is leveraging thread teams launched with a team policy. You get these teamwork, a work set for a team is kind of processed by a team, and you can use, nested parallel force and produces and scans with team thread range, thread vector range, and team vector range. And you can restrict execution of specific instructions with a single statement. Note that calling a wrong single statement inside of a nested loop, right? Say call the per thread thing inside of a vector loop and or the per team thing inside of a team thread range gives unintended results, right? Because we do not specify which thread will execute that. So it's kind of random. As in principle, it would be totally correct Kokkos implementation, which would give you, a random guy who executes that. So let's go to the next slide. With that, I come to the end of this short introduction, and we're going to switch over to actually trying the hands-on exercises. We didn't cover many things, right? We didn't cover the full build system, like the exercises we usually use, like this, kind of inline build with makefiles, which is only for like simple applications meant, right? Because you actually have to build Kokkos inline. Our main build system is CMake, but we also have spec support, etc. I didn't talk about non-sum reductions, right? All the reductions we had here were sum reductions, but you can do all kinds of other reductions. You can specify your own reductions. We have built-in reducers for, all the typical MPI things, max log, min log, whatever. Next one, you can actually do multiple reductions in one go. We didn't talk about tightly nested multidimensional loops, what you need for example, stencil operations. We have an execution policy for that. Go on. We didn't talk about a lot of advanced data structures, for example, the data structures which help you with like scatter add things. We didn't talk about subviews. I mentioned that, you can take like subviews, arbitrary subviews more or less on GPUs. We didn't talk about atomic operations. Oh yeah, I talked to set scatter contribute. We didn't talk about that. We didn't talk about team scratch memory. So the teams actually have like scratch memory available on various levels. And that allows you to expose things like GPU shared memory. We didn't talk about SIMD vectorization. We have a library for that. What else? We didn't talk about MPI and PGAS integration too much, and we didn't talk about tools and profiling and whatnot. All of that is available in the larger lectures. So there's ample stuff for that. Yeah, and that's another thing I didn't talk about, right? The math kernels. There's the Kokkos kernels library, which essentially has the equivalent of like kind of cuBLAS and cuSparse in it, as well as the interface, to that. As said, there's these whole lectures. All the dates obviously are completely out of date now. That was already run last year. I should update that. But basically, there's these 8 modules. First, what we covered here is pieces of the first 4 modules. Each module is about a 2-hour recording. So we talked about pieces of the first 4 ones, and we didn't talk at all about any of the second half. Right, but even the first 4 ones, they go into more detail and we cover some other things we skipped over here. Okay. As said, we have the Kokkos Slack channel. That's where you get all your answers all the time. We answer simple questions, complex questions. We answer hardware questions when we can. We actually have a lot of like the hardware people there. So we have like people from AMD and NVIDIA and stuff like that, and Intel on there who do answer questions. In particular, NVIDIA folks are really good about this. So it's a useful resource. Okay. With that, I think we can try and switch over and see if we can get stuff running on the exercises. So
how do you want to handle that? So either you share your screen and you try to go on Ascent, or Nevin try to show an example on Theta GPUs.
Yeah, I think that would be good. Nevin, can you do that? Can you?
In a few minutes, I need to take a slight break for a few minutes, but yeah, I can do that.
Okay, how about we take a break for like 5 minutes or so, and then we'll do that?
Okay.
Does that sound good? And Nevin, I can tell you a bit what I want you to show and what order, okay?
Okay.
Ben.